You wake up every morning, look in the mirror, and see something solid staring back at you. Your face, your hands, your body, all of it feels real, tangible, undeniably there. You touch a table, you feel resistance. You pick up a pen, you feel its weight. The entire world around you screams one message loud and clear. Matter is real. Matter is solid. Matter is what the universe is made of. Your whole life has been built on this assumption. Your education reinforced it. Your senses confirm it every single second of every single day. But what if I told you that everything you think you know about matter, about particles, about the solid stuff that makes up you and everything you have ever touched, is wrong? Not just a little wrong, but fundamentally, deeply, profoundly wrong. What if the particles you learned about in school, the electrons, the protons, the quarks, the building blocks of reality itself, do not actually exist the way you think they do? What if, in fact, they do not exist as particles at all? What if you are not made of matter in any meaningful sense, but instead you are energy, pure energy, just temporarily pretending to be something solid? This is not philosophy. This is not metaphysics. This is physics, cold, hard physics. And Richard Feynman, one of the most brilliant physicists who ever lived, dedicated much of his career to helping us understand this disturbing truth. The reality is that when you dig deep enough into what matter actually is, when you peel back the layers of assumptions and comfortable lies we tell ourselves, you discover something so strange, so counterintuitive, so alien to our everyday experience that most people cannot even wrap their minds around it. You are not what you think you are. Your body is not solid. The chair you are sitting on right now is not solid. Nothing is solid in the way you have always believed. You are a pattern of energy, a vibration in invisible fields that stretch across all of space, fields that existed before you were born and will exist long after you are gone. You are a temporary ripple in an ocean of energy, and when that ripple fades, you will not disappear. You will simply return to being what you always were, pure energy, dancing in the void. Does that sound insane to you? Does it sound like New Age nonsense? Good, because that means you are starting to feel the cognitive dissonance that every physicist feels when they first truly understand what quantum field theory is telling us about reality. This is the discomfort of having your worldview shattered. Feynman himself said that if you think you understand quantum mechanics, you do not understand quantum mechanics. And yet, he also spent decades making it understandable, making it accessible, stripping away the mathematical fog to reveal the raw, shocking truth underneath. Today, we are going to take that journey with him. We are going to discover why particles do not exist, why you are energy disguised as matter, and why this is not just some abstract theory, but the most confirmed, most tested, most undeniably true description of reality that science has ever produced. By the end of this, you will never look at your hand the same way again. You will never touch a wall and think it is solid. You will know the truth, and the truth, as they say, will set you free, even if it terrifies you first. So what exactly are we talking about here? What does it even mean to say that particles do not exist? After all, we have entire textbooks filled with particle physics. We have built massive machines like the Large Hadron Collider to smash particles together. We have photographs of particle tracks in cloud chambers. We can measure their masses, their charges, their spins. Are physicists just lying to us? Are they making it all up? No, of course not. But here is the problem. The word particle is a lie. It is a convenient lie, a useful approximation, but a lie nonetheless. When physicists talk about an electron, they are not talking about a tiny little ball of stuff whizzing around. They are not talking about a miniature planet orbiting a nucleus. They are not even talking about a wave in the way you think of a wave on the ocean. They are talking about something so much stranger that we do not even have a proper word for it in everyday language. An electron is not a thing. An electron is an excitation in a field. It is a disturbance, a pattern, a localized vibration in something called the electron field. And here is the kicker. That field is everywhere, all the time, filling every cubic centimeter of space in the entire universe. You are swimming in the electron field right now. It is passing through your body, through your brain, through every atom of your being. And when we say an electron exists at a particular location, what we really mean is that the electron field is vibrating at that location in a specific way. The electron is not a particle moving through space. The electron is space itself vibrating. This is not a metaphor. This is not a simplification. This is literally what quantum field theory tells us. And quantum field theory is the most accurate scientific theory ever devised. It has been tested to a precision of 1 part in a trillion. It predicts the magnetic moment of the electron to 11 decimal places. No other theory in all of science comes close to this level of accuracy. So when quantum field theory tells us that particles do not exist, that they are just ripples in fields, we have to take it seriously. This is not speculation. This is as close to proven fact as anything in science can be. But why does this matter? Why should you care that you are made of fields instead of particles? What difference does it make to your daily life? Well, on one level, it does not matter at all. You can live your whole life thinking you are made of solid matter and be just fine. But on another level, this changes everything. Because once you understand that you are energy, once you internalize the fact that there is no solid stuff at the core of your being, you start to see the universe differently. You start to understand that the boundaries between things are not as clear as you thought. You start to realize that the distinction between you and everything else is not fundamental, but arbitrary. You are not separate from the universe. You are the universe, a small part of it temporarily organized in a way that can think and feel and wonder about its own nature. Feynman understood this. He understood that the real power of physics is not in giving us new technologies, although it does that too. The real power is in giving us a new way of seeing, a new way of understanding our place in the cosmos. And what physics tells us is that we are not strangers in a strange land. We are the land itself, waking up and looking around in amazement. Let me take you back to the early 20th century, to a time when physicists were just beginning to realize that something was deeply wrong with our understanding of matter. For centuries, ever since the ancient Greeks first proposed the idea of atoms, people had believed that if you kept cutting matter into smaller and smaller pieces, you would eventually reach some fundamental building block, some indivisible particle that could not be split any further. The word atom literally means uncuttable in Greek. And for a long time, that is exactly what scientists thought atoms were. Tiny, hard, indestructible balls of stuff, like microscopic billiard balls bouncing around and sticking together to make everything we see. Isaac Newton believed this. John Dalton believed this. Even as late as the 19th century, when scientists were developing sophisticated theories of chemistry and thermodynamics, they still imagined atoms as solid little spheres. But then, something strange started happening. In 1897, J. Thomson discovered the electron. He was experimenting with cathode rays, beams of something that were emitted from metal electrodes in vacuum tubes. He proved that these rays were made of particles, tiny particles with a negative electric charge and a mass almost 2,000 times smaller than the lightest atom. This was shocking because it meant that atoms were not indivisible after all. They had parts. They could be broken open. The atom was not the fundamental building block of matter. There had to be something smaller, something more fundamental. Thomson proposed a model of the atom where the negatively charged electrons were embedded in a positively charged sphere, like raisins in a pudding. It was called the plum pudding model, and for a few years everyone thought it was probably right. But then, in 1911, Ernest Rutherford performed one of the most important experiments in the history of physics. He took a thin sheet of gold foil, only a few atoms thick, and he fired alpha particles at it, tiny bits of matter ejected from radioactive material, moving at tremendous speeds. According to the plum pudding model, these alpha particles should have passed right through the gold foil with barely any deflection, because the positive charge was supposed to be spread out diffusely throughout the atom. But that is not what happened. Most of the alpha particles did go straight through, as expected, but some of them, a tiny fraction, bounced back. Not just deflected a little, but bounced straight back as if they had hit something incredibly dense and solid. Rutherford himself said it was like firing a 15-inch artillery shell at a piece of tissue paper and having it bounce back and hit you. This was impossible according to the plum pudding model. The only way to explain it was if all of the positive charge and almost all of the mass of the atom was concentrated in a tiny, tiny region at the center, what Rutherford called the nucleus. The atom was mostly empty space, with a dense nucleus at the center and electrons orbiting around it, like planets orbiting the sun. This was the birth of the nuclear model of the atom, and it was a revolution. But here is the thing. This model, as brilliant as it was, still treated electrons and nuclei as particles, as little bits of stuff with definite positions and trajectories. And that is where the problem started, because particles like that simply cannot exist according to the laws of physics. Here is why. If an electron is really a charged particle orbiting a nucleus, then it is constantly accelerating, because to move in a circle is to constantly change direction, which is a form of acceleration. And according to Maxwell's equations, the fundamental laws of electromagnetism discovered in the 1860s, any charged particle that accelerates must emit electromagnetic radiation. It must give off energy in the form of light or radio waves or X-rays. So an electron orbiting a nucleus should be constantly radiating energy away. And as it loses energy, it should spiral inward, closer and closer to the nucleus, until finally, in a fraction of a second, it crashes into the nucleus and the atom collapses. But atoms do not collapse. They are stable. The chair you are sitting on is not disappearing in a flash of radiation. Your body is not imploding. Something is wrong. The classical picture of particles orbiting like planets cannot be right. This was the crisis of physics in the early 20th century. The old models did not work, but nobody knew what should replace them. And then, in 1925 and 1926, everything changed. Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others developed quantum mechanics, a completely new way of describing the behavior of matter at the smallest scales. And what quantum mechanics told them was astonishing. Electrons do not have definite positions and trajectories. They exist in a state of superposition, spread out over space in a wave-like pattern described by something called a wave function. The electron is not a particle moving around the nucleus. The electron is a probability cloud, a smear of possible locations, all existing simultaneously until you measure it. When you measure the position of an electron, the wave function collapses, and you get a specific answer. But before the measurement, the electron was not anywhere in particular. It was everywhere at once. This was so strange, so counterintuitive, that even the people who invented quantum mechanics could not quite believe it. Albert Einstein famously hated this idea. He said that God does not play dice with the universe. He believed that there must be some deeper level of reality, some hidden variables that determine where the electron really is, even if we cannot measure them. But experiment after experiment has confirmed that quantum mechanics is right and Einstein was wrong. The electron really does not have a definite position until you measure it. Reality at the quantum level is fundamentally probabilistic, fundamentally uncertain. But even quantum mechanics, as revolutionary as it was, still talked about particles. It talked about electrons and photons and protons as discrete localized objects, even if they had wave-like properties. It was not until the 1940s and 50s, when physicists developed quantum field theory, that the final piece of the puzzle fell into place. And this is where Richard Feynman enters the story. Feynman, along with Julian Schwinger and Shinichiro Tominaga, developed the first complete and consistent version of quantum electrodynamics, or QED, the quantum field theory of how light and matter interact. And QED told them something remarkable. Electrons are not particles, and photons are not particles. They are excitations in fields. The electron field permeates all of space. The photon field, also called the electromagnetic field, permeates all of space. When we see an electron, what we are really seeing is a localized vibration in the electron field. When we see a photon, what we are really seeing is a localized vibration in the electromagnetic field. The fields are the fundamental reality. The particles are just patterns in those fields, temporary, fleeting, but undeniably real in their own way. Now, before you click away or leave a comment, I need you to do something for me. I need you to tell me in the comments, what is the most mind-blowing thing you have ever learned about physics? Was it black holes? Was it relativity? Was it quantum mechanics? I want to know because I am always looking for new topics to dive into, new ways to explore the strangeness of the universe. And if you write your answer, it helps the algorithm show this video to more people who, like you, are curious about the deep truths of reality. So take a second, scroll down, and let me know. What blew your mind? And while you are down there, you might see other comments from people who are just as fascinated as you are, so stick around and join the conversation. Now, back to the story, because we are just getting started. Feynman did not just develop the mathematics of quantum field theory, he also developed a way of visualizing it, a way of making it intuitive. He invented what are now called Feynman diagrams, simple pictures that represent the interactions between particles, or more accurately, the interactions between fields. A Feynman diagram shows how an electron field can emit a photon field, or how two electron fields can exchange a photon field and repel each other. These diagrams are not just pretty pictures. They correspond to precise mathematical calculations. Each line, each vertex, each connection in a Feynman diagram translates directly into a term in the equations that predict what will happen in an experiment. And the predictions are astonishingly accurate. For example, the anomalous magnetic moment of the electron, a tiny correction to the electron's magnetic field caused by quantum fluctuations, has been calculated using Feynman diagrams to a precision of 1 part in 10 billion. And the experimental measurement agrees with that calculation to within the margin of error. No other theory in all of science has ever achieved that level of precision. Quantum field theory works. It works so well that it is terrifying, and what it tells us is that particles, in the sense of little localized bits of matter, do not exist. What exists are fields, and fields are everywhere. The electron field fills the entire universe. The quark fields fill the entire universe. The Higgs field, the field that gives particles their mass, fills the entire universe. You are not in the universe. You are the universe. Your body is a complex, organized pattern of vibrations in multiple quantum fields, all interacting with each other in precisely choreographed ways. When you move your hand, you are not moving matter from one place to another. You are changing the pattern of field vibrations in space. The field is always there. The pattern moves, but the field does not. Feynman had a way of explaining this that cut through all the jargon. He would say, imagine a field like a mattress, a big rubber mattress stretching across all of space. Now, if you push down on the mattress in one spot, you create a dent, a localized distortion. That dent is like a particle. It has a location. It has energy. You can push it around, and it will move across the mattress. But the dent is not a separate thing from the mattress. It is the mattress. It is just the mattress in a particular configuration. And if you stop pushing, the dent disappears, and the energy goes back into the mattress as a whole. That is what a particle is. It is a dent in a field. It is a localized excitation, a temporary pattern that can move and interact. But ultimately, it is just the field itself doing what fields do. Now, you might be thinking, okay, so particles are ripples in fields. But does that really mean they do not exist? I mean, a wave on the ocean is still real, right? You can surf on it. You can drown in it. It is not nothing, and you are right. Particles, or rather, field excitations, are absolutely real. When an electron hits a detector, something real happens. Energy is transferred. Momentum is transferred. You can measure it. You can photograph it. You can feel it if you get shocked. But the point is that the electron is not a thing in itself. It is not a fundamental, indivisible nugget of matter that has existed unchanged since the beginning of the universe. It is a pattern, a process, an event. And that pattern can change, can merge with other patterns, can disappear entirely and reappear somewhere else. An electron can annihilate with a positron, its antimatter counterpart, and both particles disappear, leaving behind only photons, pure energy. Where did the particles go? They did not go anywhere. The electron field and the positron field stopped vibrating in one pattern and started vibrating in a different pattern, the photon pattern. The fields are always there, only the patterns change. This is not just abstract theory. This has been observed in laboratories thousands of times. At particle accelerators like the Large Hadron Collider, physicists smash protons together at nearly the speed of light. When they collide, the energy of the collision creates new particles, sometimes dozens of them, flying out in all directions. Where did those particles come from? They did not come from inside the protons. The protons were not little bags full of other particles waiting to spill out. The energy of the collision excited the quantum fields in that region of space, and those excitations manifested as particles. Energy became matter. But it is more accurate to say that energy, which was always in the form of fields, just changed its pattern of vibration. Einstein's famous equation, E equals mc squared, tells us that mass and energy are equivalent, two sides of the same coin. But quantum field theory goes deeper. It tells us that mass is not a property of particles. Mass is a property of how fields interact with other fields, specifically, how they interact with the Higgs field. When the electron field interacts strongly with the Higgs field, the excitations in the electron field, the things we call electrons, have a large mass. When the photon field does not interact with the Higgs field at all, the excitations in the photon field, the things we call photons, have no mass. They are massless, but both are still excitations in fields. Both are still patterns of energy. The only difference is how they couple to the Higgs field, and that coupling determines whether they behave as if they have mass or not. Feynman was obsessed with making this clear. He would give lectures where he would say, Imagine that you are a wave in the ocean. You have a crest, a trough, a wavelength, a frequency. You are moving forward, crashing onto the shore. But what are you really? Are you water? No, because the water molecules are not moving forward. They are just moving up and down. The wave is moving forward, but the water is staying put. You are not water. You are a pattern in the water. You are information encoded in the motion of the water. And when you crash onto the shore and dissipate, you do not disappear. The water is still there. The energy is still there. It has just been redistributed. That is what you are. You are a wave, not in water, but in quantum fields. You are a pattern of information encoded in the excitations of those fields. And when you die, when your body decays and your atoms scatter, you do not disappear. The fields are still there. The energy is still there. It just gets redistributed. You return to the ocean from which you came. Now, this raises a profound question, one that Feynman wrestled with his entire life. If you are not matter, if you are just energy arranged in a temporary pattern, then what does it mean to be you? What is the self? What is consciousness? These are questions that science does not yet have complete answers to, but quantum field theory gives us some clues. Your sense of self, your identity, your memories, all of these are encoded in the specific arrangement of field excitations that make up your brain and body. That arrangement is incredibly complex, incredibly delicate, and incredibly temporary. It persists because your body constantly works to maintain it, to repair damage, to take in energy from food and use it to keep the pattern stable. But ultimately, the pattern will break down. The organization will dissolve. And when it does, the energy that made you up will go on to make other patterns, other structures, perhaps even other conscious beings. You are not a thing. You are a process. You are a verb, not a noun. Let me give you a concrete example to make this even more clear. Consider a photon, a particle of light. You turn on a flashlight, and photons stream out, billions of them every second, traveling at the speed of light until they hit something and get absorbed. We say that photons are particles, and in some sense they are. They carry energy in discrete packets, quanta, which is why quantum mechanics is called quantum mechanics. But what is a photon, really? It is not a little ball of light. It is an excitation in the electromagnetic field. The electromagnetic field is a fundamental field that exists everywhere in space. It has two components, an electric field and a magnetic field, and they oscillate together, perpendicular to each other and perpendicular to the direction of motion. When the electromagnetic field oscillates with a certain frequency and a certain energy, we call that oscillation a photon. But the photon is not separate from the field. It is the field. Now here is where it gets strange. When you turn off the flashlight, where do the photons go? They do not go anywhere. They get absorbed by atoms in the walls, in your eyes, in the air. When a photon is absorbed, the energy of the photon is transferred to an electron in an atom, causing the electron to jump to a higher energy level. The photon disappears. The electromagnetic field stops oscillating in that particular pattern. The energy is now in the electron field instead. Later, the electron falls back down to a lower energy level, and a new photon is emitted. But is it the same photon? No. It cannot be, because photons do not have identity. There is no such thing as this photon versus that photon. There are only excitations in the electromagnetic field, and those excitations can be created and destroyed at will. This is fundamentally different from how we think about everyday objects. If you have two identical red balls, they are still two separate objects. You can label them, track them, keep them distinct. But if you have two photons with the same energy and the same momentum, They are not two separate objects. They are indistinguishable, not just in practice, but in principle. There is no fact of the matter about which photon is which. And this is true for all particles. Electrons are indistinguishable from each other. Quarks are indistinguishable from each other. They are all just excitations in their respective fields, and fields do not have parts that can be labeled. This indistinguishability has real consequences. It leads to phenomena like the Pauli exclusion principle, which says that two electrons cannot occupy the same quantum state. Why not? Because electrons are excitations in the electron field, and the field cannot vibrate in the same pattern at the same location twice. It is not that two electrons repel each other and push apart. It is that the question of having two electrons in the same state is meaningless. The field can only vibrate once at any given configuration. This is why matter is solid. This is why you cannot put your hand through a table. It is not because the atoms in your hand and the atoms in the table are little hard balls that collide. It is because the electron fields in your hand and the electron fields in the table cannot occupy the same quantum states, and they resist being pushed into the same space. You feel solidity not because matter is solid, but because fields resist overlapping in certain ways. The resistance you feel when you push on a wall is the electromagnetic force mediated by the electromagnetic field, keeping the electron fields in your hand separate from the electron fields in the wall. And that force, that repulsion, is itself just an exchange of virtual photons, temporary excitations in the electromagnetic field that pop into existence and disappear in the blink of an eye. Everything is fields. Everything is energy. The solidity of matter is an illusion, a trick played on us by the way our senses evolved to interpret the world at the macroscopic scale. Feynman won the Nobel Prize in 1965 for his work on quantum electrodynamics, but his greatest contribution was not just the math. It was his insistence that physics should be understandable, that the weirdness of quantum field theory could be explained in plain language if you were willing to think carefully and challenge your assumptions. He said that the first principle is that you must not fool yourself, and you are the easiest person to fool. We are all walking around with intuitions about the world that are wrong. We think matter is solid because our hands cannot pass through it. We think particles are little bits of stuff because that is what the word suggests. But if we want to understand reality, we have to be willing to let go of those intuitions. We have to be willing to accept that the universe is stranger than we imagined, stranger than we can imagine. And the strangeness does not stop with fields, because fields themselves are not the end of the story. Quantum field theory tells us that fields are subject to quantum fluctuations, constant random variations in their strength and energy. Even in empty space, in a perfect vacuum with no particles present, the fields are never truly zero. They are constantly fluctuating, creating virtual particles that pop into existence and then annihilate back into nothing in fractions of a second. This is not speculation. These quantum fluctuations have measurable effects. They cause a tiny shift in the energy levels of hydrogen atoms called the Lamb shift. They cause a tiny attraction between metal plates called the Casimir effect. The vacuum is not empty. It is seething with energy, a roiling ocean of quantum activity. And you, your body, your consciousness, you are just a particularly stable and long-lasting pattern floating on top of that ocean. Now, what does this mean for technology, for our everyday lives? Well, almost everything about modern technology is based on quantum field theory. The transistors in your computer, the LEDs in your screen, the lasers in your DVD player, all of these depend on understanding how electron fields behave in semiconductors. The GPS satellites orbiting the Earth use atomic clocks that rely on the precise energy levels of electrons, energy levels that are determined by quantum field theory. The MRI machines in hospitals use the quantum properties of protons in water molecules to create detailed images of your insides. Quantum field theory is not just abstract philosophy. It is the foundation of the modern world, and it is all based on the idea that particles do not exist, that what we call particles are really just patterns of energy in fields. Every time you use your phone, every time you turn on a light, every time you take a photograph, you are relying on this truth. But the implications go even deeper. Because if particles do not exist, if you are just energy in a temporary pattern, then the whole question of what happens when you die becomes very different. Your body will decay, yes. The atoms that make up your body will scatter. But those atoms were never you anyway. They were just patterns in fields. And the energy that sustained those patterns does not disappear. Energy cannot be created or destroyed, only transformed. The first law of thermodynamics is absolute. So the energy that is, you will go on. It will become heat, it will become motion, it will become new chemical bonds in the soil, in the plants that grow from that soil, in the animals that eat those plants. You are not separate from the universe. You are a temporary eddy in the flow of energy through the cosmos, and when the eddy dissolves, the flow continues. Feynman himself was an atheist. He did not believe in an afterlife or a soul in any traditional sense, but he did believe in something he called the wonder of the universe. He believed that understanding the deep truths of physics, understanding that we are made of the same stuff as stars, that we are walking patterns of quantum fields, that we are the universe looking at itself, that this is more awe-inspiring, more beautiful, more meaningful than any religious mythology could ever be. He once said, "I think nature's imagination is so much greater than man's. She's never going to let us relax." And he was right. Every time we think we have figured out how the universe works, it reveals a new layer of strangeness. We discovered that particles are not particles, but fields. Then we discovered that there are 4 fundamental fields, corresponding to the 4 fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. We discovered that 3 of those forces, everything except gravity, can be described by quantum field theory. We discovered that the universe had a beginning, the Big Bang, and that before the Big Bang, the concepts of space and time might not even make sense. We discovered that the universe is accelerating, expanding faster and faster, driven by something we call dark energy, which might itself be a property of the vacuum, a constant background energy in the quantum fields that permeates all of space. We discovered that most of the matter in the universe is dark matter, something that does not interact with light, something we have never directly detected, but which must be there because we can see its gravitational effects on galaxies and clusters. And we still do not know what it is. Maybe it is a new kind of field, a new kind of excitation that we have not yet figured out how to detect. The universe keeps surprising us, keeps showing us that reality is deeper, stranger, more wonderful than we ever expected. And here is the thing. You get to be part of this. You get to live in a time when we are discovering these things, when the mysteries of the universe are being unraveled one by one. You get to know that you are not a collection of particles, but a walking, thinking pattern of quantum fields, energy pretending to be matter for a brief moment in cosmic time. And that, to me, is more incredible than any story we could make up. Okay, if you have made it this far, then I know you are serious about understanding the universe. So, do me a favor, hit the like button, subscribe to the channel, and turn on notifications so you do not miss the next video. Because we are going to keep going deeper. We are going to explore more of the strange truths that Feynman revealed, more of the secrets hidden in the equations of physics. And trust me, it only gets weirder from here. So, Where does this leave us? We started with a simple question. What are particles? And we discovered that particles, in the way we usually think of them, do not exist. They are not little bits of solid matter flying through space. They are excitations in quantum fields, temporary patterns of energy that can move, interact, be created, and be destroyed. And those fields are everywhere, filling every cubic centimeter of the universe, vibrating and fluctuating and giving rise to everything we see and feel and experience. You are not made of particles. You are made of fields. You are energy in a very special configuration. Energy that has organized itself into a pattern so complex and so intricate that it can think, it can feel, it can wonder about its own nature. And when that pattern dissolves, as it inevitably will, the energy does not disappear. It transforms. It becomes other things. It rejoins the great ocean of quantum fields from which it briefly emerged. There is no death in the sense of annihilation. There is only transformation, only change, only the endless dance of energy through the cosmos. Feynman understood this. He understood that the ultimate lesson of physics is humility. We are not the center of the universe. We are not special in any cosmic sense. We are temporary fluctuations in the quantum vacuum, patterns that arose by chance and will dissolve by necessity. But we are also miraculous. Against all odds, against the relentless march of entropy, we exist. We think. We create. We love. We ask questions about the universe, and, sometimes, we even get answers. And the answers we get are stranger than we could have imagined. The universe does not care about our intuitions. It does not care whether we find it comfortable or comprehensible. It simply is in all its quantum weirdness, all its field-theoretic glory, all its breathtaking complexity. And our job, as thinking beings, is not to impose our preconceptions on reality, but to let reality show us what it truly is. That means being willing to accept uncomfortable truths. It means being willing to say, particles do not exist, even though every fiber of our being wants to believe they do. It means being willing to say, I am not solid, I am energy, even though that feels like nonsense. It means being willing to follow the evidence wherever it leads, even if it leads to conclusions that shatter our worldview. Because in the end, truth is more valuable than comfort. Understanding is more valuable than ignorance. And the truth, the deep truth revealed by quantum field theory, is that you are not what you think you are. You are not matter. You are energy, pure energy, temporarily organized into a pattern that calls itself you. And when the pattern fades, as all patterns must, the energy remains, eternal and unchanging, ready to form new patterns, new structures, new possibilities. You are a wave in the ocean of existence, and the ocean is infinite. Feynman spent his entire life trying to help us understand this. He stripped away the jargon, the unnecessary complexity, the mathematical obscurity that often hides the real beauty of physics. He showed us that you do not need to be a genius to grasp the fundamental truths of the universe. You just need to be willing to think clearly, to question your assumptions, and to accept what the evidence tells you. And what the evidence tells us, unequivocally, beyond any reasonable doubt, is that the material world is a mirage. Particles are a convenient fiction. Fields are reality. Energy is reality. And you, miraculous you, are energy disguised as matter, walking around and experiencing the universe for a brief moment before returning to the infinite field from which you came. That is the truth. That is what Feynman revealed. And once you see it, you cannot unsee it. The world will never look the same again.